Even though I've known the rules of chess for a long time, when it comes to my actual skill level, um, let's just say I've never been the sharpest tool in the shed. A few weeks ago I started looking for tips on how to become better at chess, and there are many ways to improve. Reading books, chess clubs, online courses, but the thing that interested me the most was the chess analysis. The chess analysis is the process of comparing your moves with the moves suggested by chess engine. Thanks to it, we can learn patterns and avoid making the same mistakes in the future games. Even practicing against yourself with the help of the chess engine can improve your decision making and develop better intuition during the game. At least, that's what they say. And it's quite easy when you're playing online, but analyzing a game from a physical chessboard is a whole different story. You need to write down every single move, yours and your opponent's, which means you have to know the chess notation first. Then you transfer all of it to a computer with no room for errors. And games can easily go over 100 moves, so that's quite a lot of writing. Then you can upload the game to the online chess engine, assuming you find a free one. The whole process is so slow, it's just tedious. And on top of that, the human error can easily sneak in. I really like practicing against myself on a physical chessboard. So, do I really have to repeat the whole process every single time? I might not be the best chess player, but there are other things I do pretty well. Time to make that count. My idea was to build a pipeline that automates the whole process. A webcam captures all the moves during a live game and passes them to the backend so it can create a mirror of the current position on a digital chessboard. Then every position gets converted into a special notation and sent to a chess engine, which is doing a simple analysis live. And once the game is finished, you can copy the full game record without manually writing down any moves. So let's start from the B. Actually, I've started from the very end. The first step was setting up the core component of the system, the chess engine. I checked the results table from a couple last top chess engine championships, and one engine kept showing up more than the others. Its name was Stockfish. It turned out that one of the strongest chess engines out there is actually an open source project that you can run locally on your machine. I download the right version of it, then spend some time going through the documentation, mainly this section here, and finally I placed all engine files along with the X into the project tree. Communication with the engine is handled through the UCI protocol, which is an interface that allows chess engines to exchange information with a compatible GUI. In my case, I used Python, which obviously has a dedicated library for this, which transforms the engine's raw instructions into programmable API calls. Using FastAPI, I wrote a script that launches Stockfish as a sub-process. Server passes state of the chessboard to engine through the endpoint, which includes fenstring, a compact notation encoding the position of every piece on the board. Then engine returns an evaluation of that position, along with the sequence of the best moves to play, known as the principal variation. And it looks like this. Okay, let's see if the evaluate endpoint works. On the right side I have this analysis chessboard from the Lichess, and this is the site that generates a random fan. So let's copy that. Let's paste it here. And as you can see, we have the same position of the both chessboards. Now let's send that fan to our locally hosted Stockfish, and we've got the mate in 3 moves after the analysis. So let's turn on the analysis of the Lichess site, and this is also a mate in 3 moves. So let's do the moves from the principal variation to see if the analysis is correct. Now it was time to set up the front end. Using Vite as my bundler, I spun up the React project and added 2 essential libraries to it, Chess.js and React Chessboard. Then I connected both servers and moved on to crafting the graphical visualization for the engine analysis, which I created before. I added a form for inputting the engine parameters an evaluation bar displaying advantage in centi-pawns, and a field for entering the position. Thanks to the React chessboard library, I managed to integrate the virtual chessboards too. And on top of that, I added an arrow highlighting the best move, as well as the ability to flip the board for a better view. In this concept version, the flow is very simple. You just paste the position you want to analyze, and the engine returns the evaluation along with the best move, which is displayed on the digital board. From here, the goal is to replace the manual notation input with automatic move tracking, and add a move recording so that the full game log can be exported once the game is over. The input to the entire system is of course the camera. Since I don't have a webcam of sufficient quality, I decided to use my old Android phone. With an app called IP Webcam, I turned it into a device that streams motion JPEG over the local network. I added the camera configuration to a separate config file, making it easy to update things like the IP address whenever needed. After that, I created another backend endpoint responsible for capturing a single frame from the camera stream. But before we can do anything useful with that image, it needs to be recropped, reshaped, and preprocessed. Specifically, we need to detect two things: the outer boundary of the chessboard and the edges of each individual square, so that we have a precise access to every single cell on the board. Initially, I wanted to use pre-built computer vision framework called YellowV8 made by Ultralytics. It's an open source AI tool specialized in object detection and image segmentation, and it seemed perfect for my case. On platforms like RoboFlow you can find dozens of pre-trained models for chessboard detection, ready to download and plug it straight into YellowV8. Unfortunately, after a lot of time and effort, that approach completely fell apart. Every model I tried either performed terribly or didn't work at all. I suspect the culprit was either a misconfiguration in my YOLO settings or my hardware. Either way, I had to scrap that idea and take a completely different approach. Instead, I hosted a static page from the backend that collects the position of the chessboard's four corners as 2D image coordinates. Then, these are passed into a preprocessing algorithm that uses a homography matrix to straighten the board, essentially projecting the selected region onto a flat rectangle. This corrects any perspective distortion introduced by the angle of camera. As a result, each square on the board gets a consistent size and position, and perpendicular faces. At the end, the newly cropped and corrected board is then scaled to 640 by 640 pixels and ready for further operations. Now, I needed a bridge between the computer vision side and the chess engine application from chapter 1. Before building the actual detection model, I needed a tool to generate a new fan after every move. I will explain why later, but now the concept is straightforward. Every chess game starts from the same known position. Now let's convert the chessboard into an 8x8 matrix, where each square is labeled and put all the pieces on their starting places. Okay, now imagine I feed the system with a move, for now manually, something like e2, e4, which representing a piece moving from the occupied square to the empty one. First, the system checks that the right color is moving and that the move is legal according to the chess rules. Then it updates the matrix. Square e2 is marked as empty, and the piece, in this case a pawn, is moved to a4. With the matrix updated, the system generates a new fan string by scanning it line by line, left to right, following the standard fan formatting rules. So, it's not that complicated, right? I just simply implemented it in Python and added a few endpoints to handle the parser. The first operation is a reset post, request that assigns an initial fan notation to the digital board. This ensures the chessboard always starts from the clean, predefined position. Next, the get state. Endpoint reads the current board configuration along with the additional metadata, whose turn it is, whether the king is check or it's a checkmate, and the full moves history. The third endpoint is move. It triggers the parser directly. It accepts the string describing two squares simulating a piece being shifted from the one to the other. If the parser validates the move, it returns true along with the updated fan, reflecting the new position. Now I'm feeding the system with a sequence of moves, specifically one of the variations of the scholar's mate, and then query the state endpoint to inspect the exact game state. As you can see, we've got the fan describing the position after 5 half moves. Let's throw it into the Lichess analysis board to verify if the moves were passed correctly. The queen lands exactly where it should, and the final capture, delivering checkmate, was read without any issues. According to the state endpoint, the game is over. The engine detected mate. We also have a full access to the moves history at this point. The parser is working correctly. That puts me significantly closer to finishing the project. There is one remaining problem though. The parser expects a move in a specific format. Based on that, it rebuilds the piece matrix and generates fan from it. At this point, we need the last piece of puzzle, a component responsible for forming and submitting a move to the parser, not from the keyboard but directly from the system primary's input, the processed camera feed. So, we return to the cropped camera frame. Using the known dimensions of the image, we are able to map the position of each cell. Using math, we can determine the coordinates of its corners. Then we're fragmenting the large chessboard image into 64 fields, 80 by 80 pixels each. Each field will be analyzed by a CNN, a trained binary classification model that determines whether the field is occupied or empty. For each segmentation, the system built two occupancy matrices, one collecting fields marked as occupied, the other collecting fields marked as empty. Both carry appropriate labels with the field coordinates. The system remains on standby until the new camera frame enters the pipeline. Then my neural network repeats its analysis across the old chessboard cells and allocates the fields into a new pair of occupancy matrices. After each sorting pass, the two last matrices are compared against each other. The comparison immediately reveals which fields have changed state. And using the delta of these two matrices, the system assembles a string containing a field labels and sends it to the parser. When the system detects a capture where one square disappeared and none appeared, it kicks off a disambiguation routine. It starts by asking the parser for all legal captures from the source square. If there is only one possible destination, the system grabs it immediately and generates the move. But if there are multiple candidates, let's say queen disappeared from d4 in that position, a parser comes back with 3 potential destinations, and then it goes straight to the raw images. For each candidate square, it crops the corresponding region from both the before and after frames, and runs a mean absolute error comparison, pixel by pixel. Okay, so let's create MAE formula from the scratch, and it is the mean value. So first we divide, and we divide by n, because the n is the number of pixels in each image. Then we take a sum of n elements when we are indexing from 1 to n. But what exactly are we summing? We are summing the absolute difference between corresponding pixels from two images. So let's create our pixels. Now let's make them corresponding. One and the second. Okay, but the thing is, the first pixel is from frame before the move, and the second one is from frame after the move. And every pixel got its value. So by comparing them, we can measure how different they are from each other. And the full difference we're computing is producing a single score that describes how different two images are in terms of color. So the system selects the candidate with the highest MAE score, then it constructs the right move and passes it to the parser. On top of that, in the move detector I also implemented a logic to handle 3 special cases: castling, pound promotion, and en passant captures. With the working parser and move detector already in place, the only thing left was training my own binary classification model and plugging it into the pipeline. The dataset is the foundation of any machine learning model. In my project, I identified 2 possible paths. Either download a pre-trained model from web and fine-tune it using photos captured on my board, or build a completely new dataset tailored specifically to my chessboard and pieces. And given prior issues with pre-trained models for detecting chessboard contours, I went with the second option. The hardest part of creating a custom dataset is the time it takes to prepare it. A model needs thousands of properly labeled samples, and traditional manual labeling would be unbearably tedious and error-prone, so I had to find a way to automate another process. Instead of manual labeling, using components already present in the system, I built a data collection pipeline. It relies on parser's ability to determine occupancy matrix directly from fan notation. I wrote another static page that simulates the chess match. To gather data, I first make the move on the physical chessboard, then input that move into the field on the page and hit enter. And that's pretty much it. From here, the parser takes all the job. It starts from the base fan. First, it reads the move and validates its legality, then creates a new fan and builds the new occupancy matrix. The collection pipeline grabs a frame from camera and splits it into 64 squares. Based on current occupancy matrix, any square the parser marks as containing a piece gets routed to a occupied folder, while squares flagged as empty land in the folder named empty. So typing a single 4-character input automatically creates 64 labeled samples. More samples mean better results, so I added a data augmentation step as well. First, to avoid dark cell borders and pieces bleeding in from neighboring squares due to the camera perspective, each patch is cropped by 10 pixels on every side. Then there are generated 4 copies of each square. Each augmented copy is assigned to a randomly generated combination of transformations, such as brightness changes, blur, horizontal flip, or artificial shadows. This means a single move on the board produces 320 labeled samples, and as the result, dataset grows quite rapidly. Using that pipeline, I collected over 60,000 images of samples gathered under all possible lighting conditions and shadows from different angles. And with that, I was ready to train the model. Using PyTorch library in Python, I created the model architecture. A grayscale image passes through 3 convolutional blocks. Each one applies more filters, gradually building up feature maps, matrices that store what each filter detected. The first layer looks for simple things like edges and brightness transitions. The deeper ones starts already with that information, and they are focusing on more complex patterns like contours and outlines of shapes. The result then flows into the fully connected layers with dropout and a sigmoid, outputting the probability of square being occupied. My goal was to transform a rough image into a tensor carrying the actual characteristics of object, allowing the model to detect increasingly complex shapes and ultimately recognize whether a square is occupied or not. Training runs up to 50 epochs with early stopping, meaning training halts itself if the model shows no improvement for 15 consecutive epochs. To make everything run as fast as possible, the trained model is exported to Onyx format, delivering a 2 to 3 times speedup over PyTorch and CPU, which matters because we are classifying all 64 squares in real time. Once the architecture was ready, I kicked off the training script. The final results showed 99.8% of validation accuracy with very little train and validation loss. Both those values being this close to each other is a strong sign that no overfitting occurred. The model achieves great accuracy while actually working on the new data, not just memorizing the training set. Okay, all components of the system are ready, so it's time for the demo. I started testing by recalibrating the chessboard once again. Then I set up the pieces and reset the game state in the system. Using the snapshot debug endpoint, I pulled the current camera frame along with the occupancy mask generated by my binary classification model. As you can see, all squares were labeled correctly. Every square with a piece on it has a score of 1, while another square received a value above 0, which indicates the detection is working perfectly. Now I'm starting the detection worker, the component that cyclically captures frames for classification and looks for changes between consecutive frames. Then I made the move E2, E4 on the physical board. Here's the snapshot from the warped JPEG endpoint, and here's the mask according to the applied occupancy matrix. I verified that the detector picked up the move I made by checking the state endpoint. As you can see, a new fan was generated and the move E2, E4 appears in the game history. So backend is officially tested. Time to adapt the frontend to the new functionality and run the test game. The frontend adjustments took longer than I expected, but that's because I decided to add a few extra features. Some that make the system easier to use, and some that expand the services it offers. Now let me show you how the whole application works in practice. Alright, so this is the graphical user interface of my application. I've got it split into 2 tabs, one for analyzing the live game, and one for analysis of a single chosen chessboard position. So let's start with the main one. To get things going, I just hit start, and I wait for the old modules to load up. As you can see, the engine's already gotten its first position to analyze. We've got a fresh score showing up on the evaluation bar. Over here, we can see some game parameters, the current fan, whose turn it is, the move count, and the current status. The game in progress message is basically telling me that I'm good to go. I can start moving pieces on the physical board now. So let's make our first move, and after a brief moment, the move gets transferred over to the digital board. We got a new position with a fresh stockfish analysis, and among the game parameters show up the move history, along with the copy button, and I think you can probably already guess what the one is for. Now let's check how the system handles piece captures. After black plays a pawn to the center, I capture with the white pawn on the e5. And as you can see, after a moment I get the analysis of the new position. The move detector correctly registered the capture, and the frontend now shows the material advantage on the board. Now it's time to move a piece other than the pawn, let's say a knight. And as you can see, the system correctly detected the knight jumping over other pieces, which means the parser is working correctly. In the interface, I've also got a couple of simple tools, already implemented the boat rotation and the option to show in an arrow pointing onto the engine's best move. The newer feature here is the full screen mode. In this mode there is nothing to distract you, so it's just the board and the evaluation bar, so you can just really focus on the chess. Sometimes, during a live game, the engine recommends a move we just don't understand, and that's totally normal. The machine is calculating every variation of the position and predicting what move will be the best. Even grandmasters wouldn't think of moves that good on their own. To help make sense of harder positions, I built the static tab. Here, I can bring over the fan from my live game and then adjust the engine parameters as needed. For example, I can weaken it a bit so its calculations simulate a player with lower skill level. Now, thanks to the React chessboard library and simple drag and drop, I can play out a few different variations of the same position to see how they evaluate shifts compared to the engine's main line from the Live Analysis tab. The main goal of this project, besides live game analysis, was automatic transfer of the game record to the computer. Now it's time to show off that functionality. What you're seeing here is my test game, and as you can see, the latency between the physical move and it showing up on the digital board is somewhere between 3 and 4 seconds. My guess is the bottleneck in the system is the connection between the camera and the software. But honestly, I think that delay is pretty acceptable, and once the position updates, the new analysis appears pretty snappy. Of course, the moves I'm playing here are pretty far from what the engine would actually recommended, but at this point I'm less concerned about accuracy and more focused on wrapping up the game quickly. Since I don't want to speed up the game just to show off, I want you to see the app running at its natural pace. This is a good moment for me to say thanks to everyone who stuck around till the end. I know I probably rambled a bit here and there, or explained some things a little bit too briefly, but it's great that you guys are still here. And if you've got any other questions about the project, I'll do my best to answer them in the comments. In the meantime, we're getting close to the end of the game now. The parser passed the final position to the engine and it detected mate in 1. Of course I went ahead and played that move, which ended the game via checkmate. Once the game status updates, I can use the button next to the move history container to copy the game record, this time in PGN notation. And from here, I can either add it to my own personal game bank or paste it onto some external tool to break down the whole game, move by move, in way more detail. That means the planned functionality of the app has been fully delivered. I consider this project done. It took a lot of work and time, but along the way I also learned a ton of new things. Follow your passions and don't be afraid to combine them. That's where the good stuff happens. Check out my LinkedIn or my website to stay tuned with my new projects, and see you soon in the next videos. Oh, and one more thing. This is my official contribution to the live internet theory. Take care, you all. Bye.